Okay, so our 3 dB frequency is 1 over 2 pi RC, and our omega naught is 1 over RC. The capacitor times the equivalent Thevenin resistance that that capacitor sees. Okay, we're going to go back and review Bode plots because I know everybody loves them. And I rearranged these slides to get rid of the match game stuff. It just made things easier for me. A pole, remember, is places where the frequency, if I have a 0 in the denominator, it causes the whole function to go to infinity. So this is, poles are in the denominator, and this would be a pole at 100 radians per second in standard form. And the 0 is in the numerator, and it's places where when that goes to 0, the whole function goes to 0. And these are usually done as factors. If we plot them, what we get is this beautiful straight line approximation. When I get to whatever this frequency is here underneath S, when I put it in standard form, that is what I call my 3 dB frequency, because the gain is actually down by 3 dB at that point. But when we do the straight line approximation, we ignore that. So if it goes up, if it goes down, it's a pole because poles fall. If it goes up, it's a 0 because zeros float. That's the only way I can remember it. Otherwise, my polarity issues make it go wonky. The slope on these lines is 20 dB per decade, is the way I usually do it. And a decade is a increase by a factor of 10 in frequency. So going from 100 to 1,000 is a decade. And you can see that in that amount of time, in that amount of frequency, it's gone up by 20 dB. Another factor of 10 gives me another 20 dB. Okay. Everything we're going to do in here looks like a low pass or high pass filter, like in the normal world, unlike some of the stuff we do in 280. Now, there are different types of factors we can have in a transfer function. It's usually a collection of factors over another collection of factors, and we factor it by S. The simplest we can have is a constant, and this constant is going to represent things like gain. So this is saying I have a gain of 40. There's a constant term in there. Simple poles and simple zeros, these are what you usually see. This is a simple pole. If this is what my entire transfer function looks like, what I have here is a low pass filter. It passes low frequencies, it attenuates higher frequencies. To get a high pass filter, I need a combination. I need a 0 and a pole. Yep, we'll get to that. If I have a pole at an origin, this is simply something, I don't know what this is doing here, that's just stupid. I have, sorry, I don't have time to rewrite these slides every semester when I have daylight moments. And I didn't write that in the first place. This is something, a factor like S. And S could be in the numerator and S could be in the denominator. So I either have 1 over S, or I have S, or I have the dreaded 1 over S squared, which is never stable. I can have these complex conjugate pairs of poles or zeros. The standard form is a little bit weird, but when we put it in standard form, the number here, this is 1, the number here underneath the J omega or the S squared is my omega naught. This term right here just leads to a snake. It's a damping factor. If you take a controls theory class, you will learn about that. We're not going to worry about that too much for this class. Now our complex frequency, you can remember from 280, is usually written as S, like in the Laplace transform world. It's a complex number, so it has both a real and imaginary part, sigma plus j omega. We can write signals as e to the st, or like e to the sigma plus j omega t, and we can, by the laws of exponentials, we can say that's like e to the sigma t times e to the j omega t. We use this a lot in mathematics because they produce, if we have signals like e to the st, we can solve the differential equations. Major advantage. Real world signals, you can't always solve the differential equations. You have to use numerical methods. And we can also model a whole bunch of different types of signals like this. We can model DC signals, have omega equals 0. And this is the omega equals 0 axis right here. So if omega equals 0, I can have a DC signal. If sigma is positive, I can have an exponentially growing function. We generally avoid those as engineers because they lead to fires. If sigma is less than 0, I have exponentially decaying functions, which you see a lot of. If sigma 0, then I have something that looks just like e to the j omega t. That's a phasor, just like it was in EE188. So these are going to be things like sines and cosines, which look exactly the same to me because one's just the other shifted by 90 degrees. And if I look on them on an oscilloscope, I have no idea which one's which. Depends upon where I define t equals 0. So there's kind of there, and it's like kind of like an arbitrary difference in a lot of ways. I can get, sorry, if my whatchamacallit, if my sigma equals 0 is this axis, I can get either DC or I can get sines and cosines down here. Now, if I combine exponentially decaying functions with sines and cosines, I get these exponentially decaying sines and cosines. These are really common, and you see these a lot in the real world. And you can also have the dreaded exponentially growing sines and cosines, which always lead to fires. Now, because there's so many problems with fires on the right-hand side of this graph, controls engineers, when they draw their diagrams, they just leave it off. It doesn't exist because I'm not going to build anything that's going to exponentially grow with time. And they talk about that as being the right half point. And when they draw their charts, they keep them all in the left-hand plane or on the axis. Things in the left half plane are stable. Things on the axis are marginally stable. We want stability in the world, especially with bridges and heating and cooling systems and cars. We don't want them to exponentially start. Yeah, all kinds of things like that. Stability is good. Thermal reactions inside a boiler when they go, well, people die. Sorry. So Euler is the one who said, well, this e to the j theta is just the cosine of theta plus the square root of -1 times sine theta. And e to the minus j theta is cosine theta minus j sine theta. We killed this in 325. If I add these two together, I get 2 cosine theta plus j sine theta minus j sine theta, and j sine thetas go away. I can just get an expression for cosine theta that looks like this in the terms of imaginary exponentials. So those cosines and sines are imaginary e to the j, e to the imaginary number types of things. Yeah. This is one of those things that, yeah, I saw this in school, and every time they brought up, when I was an undergrad, every time they brought up Euler's formula, I just kind of like zoned out and just said, why would anybody do this? And then I started teaching 188, and I realized I have to learn this. Wasn't something you used a lot as a working engineer. We didn't use Laplace transforms a lot either. It was we used fast Fourier transforms because you can take a fast Fourier transform of a real signal that doesn't look like a nice sinusoidal wave. You cannot do Laplace transforms on messy signals. There's no mathematical expression for them. And a lot of people, it was like some communications engineers thought in the frequency domain, and data acquisition engineers thought in the time domain. And there was no going back and forth between there. You were either doing one or the other on whatever project you were working on. Okay, oh, why did that get messed up? I'm gonna fix that again because I just fixed this today. So in the S domain, this is just like we did in 188 and in 280. We found that there were impedances associated with capacitors and inductors that we can easily calculate to make the circuit analysis in the S domain, in the frequency domain, easier. So if I have a time varying signal, I'm an S domain, frequency domain type thinking of an engineer, I'm going to think of these as being impedances. ZR is always R. ZC we can write as 1 over SC, which is the same thing as our 188 version, 1 over J omega C, which is the same thing as minus J over omega C. I usually use the S after you get 280 and beyond because it's one less letter to write. And I use S and J omega often interchangeably because I'm not dealing, most of the time we're dealing with sinusoidal signals or something that's varying with time. If I want to find the impedance of an inductor, it is S times L, which is just J omega L. So we could go through this circuit and we could calculate what V out of T is just using a voltage divider rule once we know the impedances. So same kind of thing works. My V out of T is going to equal my Vn of T. Wait, this isn't of T, this is going to be of S. Vn of S times, I thought I was being so smart by putting the T's in. The impedance, I want the voltage across, SL, over the sum of all the impedances, SL plus R plus 1 over SC. And if I wanted to find the transfer function relating the output to the input, if I didn't know what the input was, or maybe the input's variable with time, I would call this V out over Vn. I just divide this equation by Vn, and I get SL over SL plus R plus 1 over SC. We're going to multiply that by S over S and divide by L. Why did we do that? To get it into a more standard form. And off of this standard, this is like a cousin of standard form. Right here, we can read out our omega naught is the square root of that term right there. It will work. It will transfer into standard form. And pretty much any LC circuit that you can find, this works. If it's an RLC circuit, it's amazing how this works. How many arguments I've won by saying, well, what's the frequency? It's 1 over root LC. Oh yeah, of course. So this, it always turns out to be, whether it's a series or a parallel circuit, if you're dealing with RC circuits, your omega naught is 1 over RC. If you understand this equation, this is like the key for everything that follows. We're going to get into a lot of we're going to get into some semi-complicated terms, but it always is going to come out. We're going to have a pole. For each capacitor, we're going to have another pole. And the pole is going to be C times the equivalent resistance that that capacitor sees. And that always works. Yeah.
Sorry. So in this case, those omega naughts, top ones for inductive capacitors and the bottom ones for RC.
Yeah. And inside of a microelectronic circuit, it's nearly impossible to build inductors. And I was talking about one today. It's an MRAM where you have to do special processing on top of the CMOS circuitry to get the magnetic elements in there. So pretty much inside an integrated circuit, we're talking about R's and C's. Inside of most electronics, we're talking about it being dominated by R's and C's, because when the magical triangle was invented in the 60s, the op-amp, at that point, you did not need inductors to do analog circuits. You could get that extra pole in there with the op-amp. So we like our R's and C's. Inductors are big, bulky, and expensive, and they don't really exist.
In this case, ES is just the transfer function rewritten into J omega.
E of S. Where's G of S? Yeah, it is.
Well,
It's,
about E of S for volts.
oh yeah, this is a J omega form right here. That's like the standard form for Bode plots.
What the function itself is the transfer function?
Yes.
Oh.
And we could replace all the S's with J omegas. Yeah. There's gotta be, yeah, okay. Now, if we look at this, what we have here is we have, oh, thank goodness, it's just this thing acting up again. Oh, what, oh, I found a trick. Try this. Yes. There's two buttons that have no unknown. It was never explained to me. There was nothing to tell me what these buttons are for. But if I accidentally hit the buttons, I think that's what's turning it off. And I think I can accidentally hit the buttons and turn it back on, or on purpose. Okay. Sorry, it made my life easy, my technological life much easier. So the factors we have here, we have this S squared term. This is like having 2 zeros at the origin. And having this right here, this term right here, is having a quadratic or having two poles. A quadratic is like having a double pole. And the frequency of that is 1 over the square root of LC. Because that term's going to be squared. Okay. And we plot this. We use Mathematica, believe it or not. I didn't do this. To plot these poles and zeros. Notice this is like a good controls engineer. The right half of the plane doesn't exist. It's not even drawn as part of the axis because it's unstable. I have 2 zeros at the origin. These make marginal, wait, does it? No, it makes it unstable. And I have a complex conjugate pair of poles. And we can plot this, and as we get close to those poles, if I made a finer mesh in here, those would get closer and closer to infinity. Because it's just the reason why they don't go up all the way to infinity is because I'm doing this discretely. I'm going to one step and calculating the value, and I'm going to another step, which isn't exactly at that where it goes to 0, and I calculate the value. So you get things that peak and gain. as you get close to there. It's a 3D plot, and you look confused. You look like you're going to ask a question. Okay. Okay, yeah. Well, we can put it this way. We've got basically, we've got the envelope of this. This is the imaginary axis right here. This is the real axis right here. And the dimension going up is the magnitude. So the magnitude's increasing, and it's peaking right at those poles. And this place right here, where the imaginary axis is at 0, is where I have the zeros. The real and the imaginary both. Okay. Its symmetry, we only look at positive frequencies. I don't know what the word negative frequency means. What is an imaginary frequency? Well, it's the imaginary axis. So, oh, that would be things that are like sines and cosines. The real axis is things that are exponential. So we go back to this plot right here. So this has, these complex conjugate pairs have both a real and imaginary part. This is -1. So it's a decaying exponent. It's a sinusoid that's decaying exponentially in the time domain. And then we have something that looks like the bat wings. Sorry, I spent too much time looking at that. Okay, the thing that we're gonna, if we plot these transfer functions, the linear magnitude of G versus the frequency, we get things that are hard to describe. Bodie was the one who, the slide rule genius, that came up with the idea, if I plot the magnitude of the frequency on a, in dB, so it's a logarithmic function on a linear scale, and on the x-axis, I put the frequency, a linear frequency on a logarithmic scale, I get things that look like straight line approximations. This is a convention for plotting these frequency response plots that still exists. If you plot something in multisim, it puts it on a Bodie plot scale because it helps people learn how to read this. Right here, I mean, just looking at this, I know I have something, some kind of pole. It's going up. It's going down. I have a high pass filter. I have something that looks like this. And my omega naught here is 0.3. So 0.3 times 2 pi. That was a frequency axis. I can write the transfer function just looking at that. It's a high pass filter. You see things that look like high pass filters and low pass filters quite a bit. An op amp actually looks like a low pass filter. Its frequency response is going to roll off at some frequency. 741s, it's a very low frequency. They're good for audio. That's about it. If that. That's kind of useless. Okay, so we've got the two most basic kind of filters we can think about. This one, right, and let's think about this. At low frequencies like DC, caps are open. So if we're thinking about DC and this cap being open here, what that would say is my very low frequencies are just going to pass through. So this one is a low pass filter. And if I look at this one and my cap wasn't open, then if I put a low frequency in at VN, I would have no connection to the output. So this is a high pass filter. And all you've done between the two of them is change the position of R and C. Now we're going to figure out the poles and zeros. How much time do I have here? I'm pushing this a little bit because I want to get done in 3 days. So for a low pass filter, the transfer function always looks like this. A single pole low pass filter. It's always like this. This is like the most important Bode plot to know. I've got some K here, and the K, the value here would actually be 20 times the log of K. In this case, K must equal 1 for that plot. So I start out here. When I get to whatever my omega naught is, I'm going to be, my actual function is going to be 3 dB below where it's at. That's why I keep calling it the 3 dB frequency. But my Bode plot approximation is just a straight line. And beyond that point, every time I increase by a factor of 10, I am going to go down 20 dB. Really good Bode plot to know. Most important one you can do. Now, if you look at the slope here, it says minus 20 dB per decade. And that's what I always used. And there were some old engineers who like to use 6 dB per octave. It means the same thing. It's the same slope. An octave is a factor of 2 in frequency. A decade's a factor of 10. And it comes out to be about the same. The phase plots, I'm going to get a 90-degree phase shift, and it takes 2 decades to go through there. It starts at 1/10 of omega naught, goes out to 10 omega naught. Okay, low pass filter.
Is the 5.7 supposed to be like a noise margin or a margin of error or something like that?
5.7. 5.7. Oh no, the 5.7 degrees is how much error you have.
Oh, okay.
Yeah, because when you do the straight line approximation, you just do this.
Right.
And there's a 5.7 degree error at 1/10, and another 5.7 degree error there.
So it is a margin.
Yeah, it's an error. If you plot things, if you have like modern processing tools and things like that, you can actually calculate these exactly in something like MATLAB, or you can calculate it exactly in Multisim or Mentor Graphics. But if you're just drawing a sketch by hand, you just ignore that 5.7 degrees, and you ignore that 3 dBs, 3 dB. But every engineer kind of has it in their head that I'm going to be 3 dB off. Or if I actually take it out in the lab and measure it, where it hits that 3 dB point, that is where the omega naught is. 3 dB less than whatever K is. I talked to a VP of engineering this morning, was trying to convince him to hire more NAU grads. There are a lot of jobs out there for analog engineers, not nearly the volume of jobs as there are for digital engineers. But the thing is, for analog engineers, there's so few people being trained who understand anything about analog anymore. And I've just been told that NAU is the best school in the state for that right now. And as pathetic as I feel doing this, and thinking about how little you guys know, at least you have some training and some knowledge of analog. And I feel like every engineer needs that, even if you're an FPGA designer or a microprocessor designer, because I see these digital guys now making really rookie analog errors that make me mad.
So it's like pretty much any other school just completely disregard this kind of analog.
Yeah, because it's so much easier to teach people to program FPGAs, and you can get jobs. There's plenty of jobs out there. But, you know, I saw the graphs a while ago. It's like there was a factor of 10 increase in the number of digital electrical engineers that they needed over from 2000 to 2010. So, yeah, a lot of people needed to be trained in that. But there was also like a factor of 2 increase in the number of analog engineers they needed. But it's harder to get It's harder to go to school for that because there's not many of us left who understand it.
Do you know the course that we have learned about BJTs, or is that just?
It's generally mostly ignored. 280, that was it.
I don't even remember talking about
It was right before the finals.
it.
Okay. So for a high pass filter, I need both a pole and a zero. I need S and I need a S plus omega naught. When I put it in standard form, it looks something like this, where this kind of comes out and becomes part of the K. It becomes K omega naught. So I have, what I've got here is I've got a 0 at the origin. And I have a pole at omega naught. And I think we did that. We did this in the 280 lab. The 0 at the origin, if you recall, at omega equals 1, it's at 0 dB. Yeah, they really did this. And so it has a Bode plot that looks like this. There's just a straight line going up. Passes through, it has a slope of 20 dB per decade, and it passes through 0 dB at omega equals 1. The other one, my, whatchamacallit, I don't want to use blue. Blue's absolutely the worst color for our slides. I want to use green. Okay, so my other one is a pole at omega naught. It will go through 0 dB, and then it starts, when I get to omega naught, it starts falling by 20 dB per decade. So those two cancel out. I got a slope of plus 20 and minus 20, and my overall is going to look like it's going to go up and then it flattens out. The thing is, without having to go through and do the math and calculate it all the time, because this gets to be a headache to calculate, the magic trick that I use to know this is that at omega naught is where that 3 dB frequency is. And it always works out like that, because if you plug in omega equals omega naught, this comes out to be 1/2, which is 3 dB. I did that on purpose in the 280 lab. But we're not going to talk about high pass filters a lot, but that's another good one to know, other than the low pass filter, which is like the golden one. So we want to be able to use all this to figure out, all that's been reviewed so far, figure out the low frequency response of the common source amplifier. For the low frequency response, we're going to have one pole for each. It's going to look like a low pass filter for every single capacitor on there. These are big capacitors. They're microfarads, they're nanofarads, and they're going to cause the low frequency low roll off. In the next class on Tuesday, we're going to look at the high frequency roll off. This looks like a low pass filter. These are tiny capacitors. These are like femtofarads, and they cause the gain to roll off at high frequencies. Okay, and it's always 1 over RC. So big capacitors, 1 over RC. C is a big number. My frequency is going to be small. If C is a small number, the frequency is going to be big. This is caused by the capacitors on the board. This is caused due to the MOSFET or the BJTs. I should say something. We talked about BJTs a little bit. There was another device that Dr. Cambeau mentioned in the last class called a JFET. And you've never heard me use the J word before. And usually when he talks about it, I call it the J word. Before we could build MOSFETs, they had this great idea of building something like a MOSFET. And instead of building the gate using a capacitor, they used a reverse bias diode. And they work really well, and they have a really high input resistance. But if you put the voltage on the gate at the wrong value, you forward bias that diode, and they just explode. So you have to be really careful with the gate voltage.
Those are on
JFETs.
I'm surprised there's not some military specification where you hit a button and it just
We do that on our puffs. We have these little tricks. If somebody tries to read it and they don't know what they're doing, it literally just destroys the device.
I remember I was paired with a couple of Austrians for 286 and we had built the ADC, which is like the second part of that.
Right.
And we used the JFET to do that.
Okay.
Like a ramp generator.
Yeah. That sounds like Sharber was involved. Yeah. I've used them before. I've used them professionally. I just don't enjoy it. Now we've got three. Okay, we've got these capacitors are here. Those are the obvious ones. There's also a gate to source capacitance, but it's really small. It's femtofarads. There's a gate to drain capacitance. It's really small. It's femtofarads. There's a gate to body capacitance. It's small. The three we're going to worry about for the low frequency response are the three that we can actually see that are drawn in the schematic. Well, I think you get to do this on the one of the pre-lecture quizzes. Somebody came in and asked me about it. And I was really unhappy with the way Dr. Brower calculated it. So what I did is I gave everybody one of the problems, so I gave everyone 3 points on that one. Yeah, teaching others is really the best way to learn. And you can, anybody who's been a lab aide or done anything like that really knows that. Believe me, it made me learn the theory behind all this. Before this, I just knew how to do it. Now, doing the analysis is not going to take any fancy circuit analysis skills. We're going to use things like voltage dividers. We're going to use Ohm's law, current dividers, and more Ohm's law. Later, we're going to do some sneaky tricks. But for right now, this is pretty much it. If you have those down from 188, this is why I want 188 to be almost a drill on voltage dividers, Ohm's law, and current dividers. Plus throw some op amps in there and maybe the power stuff that the mechanicals need. And then we could just call it a day. So I go through and I do this analysis and I come up with, oh yeah, okay, if we look at the total gain curve, V out over V sig, I could get that by taking V out over ID and multiplying that by ID over VG and multiplying that by, I agree, VG over V sig. And if I do that, my IDs cancel out, my VGs cancel out, and I get V out over V sig. So what this expression is these three things multiplied together. Disturbing, yes. Now, the way we're going to analyze this, though, is kind of makes this way easier than it looks. Is I have, for this one right here, this looks like a high pass filter because it's got the S in the numerator. And it has a 3 dB frequency at, or omega naught, at 1 over CC1 RG plus R sig. So this is going to be one of my poles right there. My second pole is going to be at GM over CS. My third pole because I got to multiply all these together, is going to be, and these are all factored already, is going to be at 1 over CC2 times RD plus RL. So you get these complicated terms, but if you know how to read poles and zeros, and you have it factored, you just have to read off what those where those poles are at. And the midband gain is going to be this times this times this. All three of them multiplied together. So if I can find out where each of those individual pole frequencies are, what I can do is I know my transfer function is going to look like this. Midband gain is where it's going to go up to. Steeper, steeper. Let's just minus 20. I need to draw this better. This is going to be omega p, one of them. This is going to be another one, omega p. There's a better picture in the next slide or so. And this is at another omega p, where the slope just keeps getting steeper and steeper as we go on. Let's find the picture like this. Ah! I will be back and we'll be on slide 29.